In this video, we're going to go over elimination reactions, E1, E2 reactions, and the E1CB reaction. So let's say if we have an alkyl halide. This is 2-chlorobutane. Now what's going to happen if we add water? And let's say if we add heat as well. Now, when you mix a secondary alkyl halide with water, the reason why it's secondary is because the carbon that has the chlorine is attached to two other carbon atoms. So that carbon is secondary, which makes it a secondary alkyl halide. When you mix this with water, two things can happen. You can get the SN1 reaction, which is a first order nucleophilic substitution reaction, or you can get the E1 reaction, which is a first order elimination reaction. Now, since this video is about elimination reactions, we're going to focus on just that. So, in an E1 reaction, the first thing that happens is ionization, the production of a carbocation intermediate. Now, which element is more electronegative, carbon or chlorine? On a periodic table, here's carbon, then you have nitrogen, oxygen, fluorine, and chlorine. Typically, the closer an element is to fluorine, the more electronegative it is. Electronegativity increases to the right, and it increases as you go up. So chlorine is more electronegative. The electronegativity for carbon is 2.5, and for chlorine is 3.0. So when the carbon-chlorine bond breaks, because chlorine is more electronegative, because it has a stronger desire for electrons, chlorine is going to pull the electrons toward itself. And that's what happens in the first step of the E1 reaction. Now, keep in mind, before the bond breaks, chlorine has 3 lone pairs. But when that bond breaks, and when chlorine gets the 2 electrons that is in that bond, it's going to turn into the chloride ion, which it now has 4 lone pairs, or 8 electrons. So the carbon is electron deficient. So it's going to turn into a carbocation. That's a carbon with a positive charge. And so that's the first step of an E1 reaction. Now, the carbocation is not stable because it has a charge. Typically, any atom with a charge usually is relatively unstable. So if you were to draw the energy diagram, you'll see that the carbocation is very high in energy. Now, the next step, or the next thing that happens in an E1 reaction, is the base, which in this case is going to be water. Water can act as an acid or base, which makes it amphoteric. The base is going to grab a hydrogen, because that's what bases do. They're proton acceptors. And as it grabs the hydrogen, the carbon-hydrogen bond is going to break, and those electrons are going to be used to form a double bond. But let's understand why this happens. So why does water go for the hydrogen? So oxygen is more electronegative than hydrogen. So oxygen has a partial negative charge. Hydrogen is partially positive with respect to oxygen. So that is the reason why water is going to go for the hydrogen, because opposites attract. Oxygen has a partial negative charge. Hydrogen has a partial positive charge. Now, when the carbon-hydrogen bond breaks, why do the electrons move towards the carbon atom? For one thing, we have this very positive charge on the structure, so it's going to pull the electrons toward it. And also, whenever the carbon-hydrogen bond breaks, the electrons are going to go towards the carbon atom. And the reason why that happens is because carbon is more electronegative than hydrogen. The electronegativity value for hydrogen is 2.1. And so whenever a bond breaks, the electrons is going to move towards the atom that is more electronegative. And so as a result, we're going to get an alkene. So that's the E1 reaction. Now keep in mind, this is not the only alkene that we can get. Water can remove the green hydrogen, or it can remove another hydrogen that's on the secondary carbon. So we can get the trans alkene product, we can also get the cis, or we can get a terminal alkene. That's a double bond at the end. It turns out that the major product is 2-butene, the trans 2-butene isomer. This is known as the Hoffman product, the terminal alkene. And this one is the Zaitsev product. I've seen it written this way as well. The Zaitsev product is the alkene that is more stable. Tetrasubstituted alkenes are more stable than trisubstituted alkenes, which are alkenes with 3 R groups as opposed to 2. And trisubstituted alkenes are more stable than disubstituted alkenes. Now there's 2 common disubstituted alkenes. You have the trans isomer and you have the cis one. The trans is more stable than the cis isomer because the bulky R groups are further apart from each other, so there's less steric interaction. And one of the least stable, or the cis is more stable than the monosubstituted alkene. And an alkene that doesn't have any R groups is the least stable, which is ethene, which is just CH2 double bonded to another CH2. The rate law for an E1 reaction is the rate of the reaction is equal to the rate constant K times the concentration of the substrate. So the overall order for an E1 reaction is first order. You can see the 1 on top. So it's a unimolecular reaction. The rate of the reaction depends only on the substrate, that is the alkyl halide in our last example, which was 2-chlorobutane. So if you double the concentration of the alkyl halide, the rate is going to double. If you triple the concentration of 2-chlorobutane, the rate is going to triple. If you increase the concentration of the base, it's not going to affect the rate of an E1 reaction. The E1 reaction only depends on the concentration of the substrate. And the energy diagram for an E1 reaction looks like this. The first step is highly endothermic, because remember we said that the carbocation intermediate is very high in energy. And the second step is exothermic. So on the y-axis we have potential energy, on the x-axis is the reaction coordinate. Here are the reactants, the products, and the intermediate, which is the carbocation intermediate. Here is the first transition state, and here is the second transition state, which is also known as the activated complex. So the reason why the first step is endothermic because you have to put in energy to go from the reactants to the intermediate, because the intermediate is higher in energy than the reactants. That's why the first step is an endothermic step. The second step is an exothermic step, because as you go from the intermediates to the products, you're decreasing, the system is losing potential energy, which means that it's releasing energy. And so therefore it's an exothermic reaction. Anytime energy is released or heat is released, it's exothermic. Now, which step is the slow step? Which step is the rate determinant step? Notice that the activation energy for the first step, the activation energy is the difference between the energy of the reactants and the transition state. Because it's so much higher, the first step is the slow step. And the rate of the reaction depends on a slow step. In this first step, we had the alkyl halide. The base wasn't a part of the first step. The base, which was water, it was important in the second step. The second step is the fast step, and the rate doesn't depend on the fast step. That's why it doesn't depend on the concentration of the base for an E1 reaction, because it's not part of the slow step. Now let's go back to 2-chlorobutane. What's going to happen if we add a strong base, let's say sodium hydroxide? Last time we added water. Water is not a strong base. Water can act as a weak acid or a weak base. But when you add a strong base to an alkyl halide, the E2 reaction can occur. So In the E2 reaction, if you use a non-bulky base like hydroxide, which is a small base, it's strong but it's small. Because it's small, it can go for the red hydrogen or the yellow hydrogen. And it can remove both, but it prefers to remove the red hydrogen because it leads to the more stable product, which is the Zaitsev product. So we're going to ignore the yellow hydrogen. Even though we can get the product associated with it, it's not going to be the major product. So we're going to focus on the major product right now. So the base, which has a negative charge, is attracted to the partially positive hydrogen atom. And as it abstracts the hydrogen atom, the carbon-hydrogen bond is going to break. The electrons are going to move towards carbon because carbon is more electronegative than hydrogen. And as a result, once the double bond is formed, the leaving group is going to leave. Now, this is going to happen all at the same time. As soon as hydroxide removes that hydrogen, the carbon-hydrogen bond is going to break instantly, the carbon-chlorine bond is going to break, and the double bond is going to form at the same time. This is called a concerted reaction mechanism. That's when all bond breaking and bond forming processes occur at the same time. And so we get the alkene in a single step. So keep in mind, we can get the other products too. We can get the trans-2-butene isomer, the cis-2-butene isomer as well, and 1-butene as well. But this is the major product, which is known as the Zaitsev product, since we have a fairly stable alkene compared to the other options that are out there. Now, if we draw the energy diagram for an E2 reaction, it's only going to have one transition state because it's only one step. So here's the reactants, here's the products, and the rate law expression for the E2 reaction, the rate is equal to K times the concentration of the substrate times the concentration of the base. So for the E2 reaction, it depends on both the substrate and the base. It's first order with respect to the substrate, first order with respect to the base, but the overall reaction is the sum of these two numbers. So it's second order overall, and thus we have a 2 here. The E2 reaction means it's a second order elimination reaction. It depends on two things, the substrate and the base. So if you double the concentration of the substrate, the rate is going to double. If you triple the concentration of the substrate, the rate is going to triple. If you double the concentration of the base, the rate is going to double. If you quadruple the concentration of the base, the rate is going to quadruple. Now, let's say if you double the concentration of the substrate and if you triple the concentration of the base, what's going to be the effect on the rate? Well, 2 times 3 is 6. So the rate is going to increase by a factor of 6. If you triple the concentration of the substrate and quadruple the concentration of the base, the rate is going to increase by a factor of 12. You need to multiply the two. So now, what's going to happen if we use 2-chlorobutane again, but this time, instead of using a small, unhindered, but strong base, let's use a bulky base, like tert-butoxide. Typically, in a test question, you might see this in the form of potassium tert-butoxide, which might look like this. And it's usually dissolved in tert-butanol. Now, because the base is bulky, it doesn't want to go for the red hydrogen because it's harder to get to. I mean, if it could, it would, but it's too difficult to approach. So it's going to go for the more accessible hydrogen. That's the hydrogen at the end, the primary hydrogen, as opposed to the secondary hydrogen. So the steps are going to be the same. The base is going to grab the hydrogen, the carbon-hydrogen bond is going to break to form the alkene, expelling the leave group at the same time. So this time we're going to get 1-butene, and 1-butene is going to be the major product, which is known as the Hoffman product, because this is the less stable alkene. So anytime you use a bulky base, it's going to go for the less accessible hydrogen, and so it's going to lead to the less stable alkene. Now, what if we use, let's say, a different type of alkyl halide, a fluorine versus a chlorine? And we're going to use hydroxide. a small unhindered base. What's going to happen? It turns out that if the leaving group is fluorine, you're going to get the Hoffman product. But if the leaving group is like chlorine, bromine, or iodine, you're going to get the Zaitsev product. So whenever you have a good leaving group, the Zaitsev product is the major product. So the 2-chlorobutane is going to give you the Zaitsev product if you use hydroxide. The mechanism is the same. However, if you use a fluorine, hydroxide is going to go for the yellow hydrogen, and it's going to give you the Zaitsev product. The question is why? Why does that happen? But make sure you know that, by the way. So a bad leaving group gives you the Hoffman product, but a good leaving group is going to give you the Zaitsev product. The answer has to do with the transition state. You see, when you have a good leaving group, it's easy to get rid of. And so the transition state is going to resemble more like an alkene as opposed to a carbanion. Therefore, whichever reaction produces the more stable transition state, that's going to be the reaction that occurs. And because disubstituted alkenes are more stable than monosubstituted alkenes, this is why we get the more stable alkene, which is the Zaitsev product. As hydroxide grabs the hydrogen, this is going to form a double bond, kick out the Cl, and so because we have that alkene-like transition state, we're going to get the most stable alkene. So anytime you have a good leaving group and a small unhindered base, you get the Zaitsev product. Keep in mind, the reason why this is disubstituted is because it has 2 R groups. And the reason why this is monosubstituted is because it has 3 hydrogens, which means that it has 1 R group. Now let's look at the other example. Let's consider the one with the fluorine. So as hydroxide approaches to grab the hydrogen, all the bonds doesn't break immediately because fluorine, it's a poor leaving group. And because fluorine's a poor leaving group, it's harder to kick out. And so as hydroxide approaches the hydrogen, you get this buildup of negative charge. And so if the transition state with the most stable carbanion intermediate, that's going to be the major product due to that buildup of negative charge. And this is why you're going to get this, the Hoffman product. Because the transition state, it resembles more like a carbanion as opposed to an alkene. Because fluorine is a poor leaving group, it takes a while for it to leave. And so as hydroxide approaches, you have a buildup of negative charge, and that's why the transition state resembles more like a carbanion than an alkene. And if you think about it, let's review carbocation stability. You know that tertiary carbocations are more stable than secondary carbocations. And the reason why that's the case is because the methyl group is an electron donating group. It can donate electron density by means of the inductive effect that's through the sigma bond, or by means of hyperconjugation, which is the overlap of atomic orbitals. And so it can donate electron density to satisfy that carbocation's quench for electrons. So tertiary carbocations are therefore more stable than secondary carbocations, which are more stable than primary carbocations. Well, it turns out that the reverse is true for carbanions. A primary carbanion is more stable than a secondary carbanion, which is more stable than a tertiary carbanion. The methyl groups are still weak electron donating groups, so they're donating electron density to a carbon that has a negative charge. That carbon which has a negative charge, it doesn't want more electrons, it wants to get rid of it. That's why a tertiary carbanion is less stable, because they're adding electron density to a carbon that already has a lot of electrons. It doesn't want more. So remember, primary carbanions are more stable than secondary carbanions, but secondary carbocations are more stable than primary carbocations. So now going back to our discussion where we had 2-fluorobutane. So here we have a primary hydrogen, and on this carbon we have a secondary hydrogen because the hydrogen is attached to a secondary carbon. Now keep in mind, we said that the transition state resembles like a carbanion. So which hydrogen is going to lead to the more stable carbanion? Is it the primary hydrogen or the secondary hydrogen? Keep in mind, a primary carbanion is more stable than a secondary carbanion. That is why hydroxide is going to go for the primary hydrogen, because it forms a more stable primary carbanion transition state. And so that's why we're going to get the Hoffman product whenever you have a poor leaving group. And so we're going to get the less stable terminal alkene. Here's a question for you. Let's say if we have a bromine atom and let's say if we have a double bond on this side, what's going to happen if we add hydroxide or sodium hydroxide to it? Where is the alkene going to form? So hydroxide is going to remove a hydrogen that's one carbon away from the bromine atom. So it can remove the yellow or the green hydrogen. Now both of these are secondary, so they both lead to disubstituted alkenes. But it turns out that the hydroxide is going to go for the green hydrogen as opposed to the yellow hydrogen because of the presence of this double bond. So as it goes for the green hydrogen, we're going to form a double bond, and then the Br is going to leave. And we're going to get a product that looks like this. Now, if we were to remove the yellow hydrogen, the product would look like this. Which product is more stable? The one on the left or the one on the right? It turns out the one on the left is more stable because we have a conjugated system. Whenever you have an alternating pattern of double and single bonds, the double bonds are conjugated and are stabilized by resonance. So here it's a double bond, then a single, and then a double. We have conjugation. So here's another example for you. Let's combine this alkyl halide with sodium hydroxide. What is the major product for this reaction? Most E2 reactions are known as anti-elimination reactions. Now, what does that mean? What this means is that the hydroxide is going to grab a hydrogen from the back. Now, let's briefly talk about why it grabs the hydrogen that's anti to the bromine. So if the bromine is here, hydroxide is going to grab a hydrogen here. It's not going to grab the hydrogen over here. The reason being is hydroxide has a negative charge and bromine has a partial negative charge. So the two are repelled by each other. So hydroxide, when it goes for the partially positive hydrogen atom, it wants to be as far apart as possible from the bromine atom. Therefore, to minimize electron repulsion, it's going to go for the hydrogen that's anti or opposite to the bromine atom. Now, you heard of the word anti when you've learned of Newman projections. So let's say this is the bromine, and here are the other hydrogens. This hydrogen here is anti to the bromine, the one in red, because they're 180 degrees apart. And so that's why E2 is considered to be an anti-elimination reaction. We want to eliminate the hydrogen that's anti or 180 degrees away from the bromine atom. So now, in this structure, hydroxide can remove a hydrogen that's 1 carbon away from the bromine on either side. The question is, which hydrogen can be removed from the hydroxide ion if we specify stereochemistry? So notice that the bromine atom is in the front. That means that hydroxide is going to remove a hydrogen that's in the back, or a hydrogen that's on the dash. So it can remove the yellow hydrogen or the purple hydrogen. Therefore, we can get a mixture of 2 products. So if we remove the yellow hydrogen, the double bond is going to form between the yellow hydrogen and the bromine atom. By the way, the E2 reaction is called a dehydrohalogenation reaction because you're removing a hydrogen and a halogen in this case is the bromine atom. So this is the product that we're going to have. And the CH3 is still in the front. Now, we can also remove the purple hydrogen because it's in the back as well. So we can get a double bond over here. So we can get a mixture of 2 products. Now, once we form the double bond, this carbon is no longer chiral because it doesn't have 4 different groups. So we don't have to put it on a wedge. We can simply leave it like this. Now, which of these 2 is the major product? Since we're using a small, non-bulky base, and we have a good leaving group, the major product is going to be the Zaitsev product. That's the one with the most stable alkene. So let's find out which one is more stable. Let's look at the 2 double bonded carbon atoms. How many other carbon atoms are attached to those red double bonded carbon atoms? So for the structure on top, there's only 2 other carbons attached to it. So this is a di-substituted alkene because it has 2 R groups. Now for the one on the bottom, it has 3 R groups. There's at least 3 carbons attached to it. So this is tri-substituted. You can also show the hydrogens. If there's 2 hydrogens, then there's 2 R groups because it has to add up to 4. If there's 1 hydrogen on a double bond, there's 3 R groups because 4 minus 1 is 3. And so the one that has the most R groups is the Zaitsev product. So therefore, this is going to be the major product. And using a non-bulky base with a good leaving group, the Hoffman product is going to be the minor product. So this is going to be the major product. That's the answer for this particular example. Now what about this example? Let's say this time the CH3 is in the back as opposed to being in front. And we're going to use hydroxide again. So what products can be formed in this reaction? And identify the major product, just like the last time. So let's draw the different hydrogens that we have. We have a hydrogen in the back and one in the front. And over here, because the methyl is in the back, the hydrogen has to be in the front. Now keep in mind, the E2 reaction is an anti-elimination reaction, which means the hydrogen and the bromine must be opposite or anti to each other. So because the bromine is in the front, it's on the wedge, the hydrogen has to be on the back or on the dash. So the only hydrogen that we can remove is the yellow hydrogen. We can't remove the green hydrogen or the purple hydrogen because it's syn with respect to the bromine. It's on the same side. There's syn elimination, SYN, and there's anti-elimination. For the E2 reaction, it typically undergoes an anti-elimination reaction. So hydroxide is going to go for the yellow hydrogen. And so we're going to get just only one product. And it turns out this product is the Hoffman product. So this is one of the rare occasions where you get the Hoffman product due to stereochemical limitations. Now, something that you must know. The E2 reaction typically undergoes the anti-elimination reaction, but the E1 reaction can undergo the syn elimination or the anti-elimination. which means that the hydrogen could be in the front or in the back. It doesn't matter. So going back to that last example that we had, in an E2 reaction, we can only form the double bond here because this hydrogen is in the front. And so we can't remove it by means of the E2 reaction. But using the E1 reaction, we can remove any hydrogen because the E1 reaction can occur by syn elimination or anti-elimination. So if we were to use like water or methanol with heat, we can get both products. The double bond can form here, and it can form here as well for the E1 reaction. So to get this product, it has to be syn elimination because these two are on the same side. Now to get the other product, it can be syn or anti because we can remove both for the E1 reaction. Now let's understand why. Let's go back to this example. So here we have a yellow hydrogen. Let's say the yellow one is in the front. Let's say bromine is also in the front. And let's say the green hydrogen is in the back. In an E1 reaction, the first step is ionization, the formation of a carbocation. So notice that the bromine atom is no longer attached to the structure. So that's why the hydrogen doesn't have to be opposite to the Br anymore, because the bromine atom is no longer attached to the carbon chain. So therefore, the base in this case, which is water, can go for any hydrogen. It can go for the green hydrogen, which is anti to the Br that was there before, or it can go for the yellow hydrogen, which is syn with respect to the bromine that was previously on the ring. And so that's where we can get the cis isomer and the trans isomer, because we can remove both hydrogens, leading to two different products. Now what about this example? So this time, the leaving group is going to be surrounded by two methyl groups. The leaving group is a quaternary nitrogen atom. Whenever nitrogen has 4 bonds, it has a positive formal charge. So it's ionically bonded to hydroxide. Now if you take an orgo 2, this is the Hoffman elimination reaction. That's what it's called. And so by its name, you know you're going to get the Hoffman product. But in this case, the Hoffman product doesn't matter, because if we form a double bond here by removing a nitrogen atom and a hydrogen, it's still going to be tri-substituted. And if we form it here, it's still tri-substituted. So the Zaitsev versus the Hoffman really doesn't matter in this particular example. But if it did matter, you would get the Hoffman product, because nitrogen is a poor leaving group. So which hydrogen will be removed? Will it be the yellow hydrogen? Now that hydrogen is in the back because the methyl is in the front. Or will it be the green hydrogen, which is in the front? The Hoffman elimination reaction is an anti-elimination reaction. So the hydrogen that's going to be removed has to be opposite to the nitrogen, which is the leaving group. So the base is going to go for the yellow hydrogen, form a double bond, and kick out the nitrogen. And so the product for this reaction is going to look like this. We're still going to have the two methyl groups, but this one is no longer chiral because it's directly attached to a double bond. So that's going to be the product for that reaction. Now, starting with a similar substrate, let's say we still had a nitrogen atom in the front that's attached to two methyl groups, and plus it has an oxygen with a negative charge. So this is a tertiary amine oxide. What's going to happen if we add heat to this reaction? For the other reaction, the Hoffman elimination reaction, you need to add heat to get it started. This reaction is called the Cope elimination reaction. It's an E2 reaction, but it's a syn addition reaction. It's not an anti-addition reaction, it's a syn addition reaction. And so the oxygen, which is going to behave as the base, is going to go for the hydrogen that's on the same side. And so it's going to go for the yellow hydrogen because it's syn with respect to the nitrogen. It's not going to go for the green hydrogen. As you can see, the oxygen is already in the right position to go for the yellow hydrogen. And so we're going to get a cyclic 5-membered transition state. 1, 2, 3, 4, 5. So the oxygen is going to go for the hydrogen. The carbon-hydrogen bond is going to break. And then the carbon-nitrogen bond is going to break as well. So the product that we're going to get is going to look like this. So we're going to have a double bond on this side this time. And so we're going to get this product. So just make sure you remember that the Cope reaction is a syn E2 elimination reaction, and the Hoffman reaction is an anti-E2 reaction. Now let's say if we have a nitrogen with 3 methyl groups. So this is the Hoffman reaction, and we still have hydroxide. Now, is hydroxide going to go for the blue hydrogen or the green hydrogen? Now, even though this is an anti-elimination reaction, it's still a Hoffman reaction. We're going to get the less stable alkene if there's a choice between the two. In the other example, it didn't matter because we can get a trisubstitute alkene regardless of which hydrogen you remove. But in this case, it does matter. So hydroxide is going to go for the blue hydrogen because it leads to the Hoffman product. And so we're going to get this product. The nitrogen atom is a bad leaving group like the fluorine atom. And typically, when you have a poor leaving group, you're going to get the Hoffman product because the transition state is going to resemble more like a carbanion than an alkene. Now consider this example. Let's use the tertiary amine oxide. So this is the Cope elimination reaction. So here we have a blue hydrogen and a green hydrogen. Now, as we mentioned before, the Cope elimination reaction is a syn elimination reaction. But because stereochemistry is not specified, we don't have to worry about the syn-anti situation. We just have to realize that the Cope elimination reaction is still a Hoffman reaction. It's not a Zaitsev reaction. So the oxygen is going to attack the hydrogen that is at the end, the primary hydrogen, rather than the secondary hydrogen, because we still have a nitrogen atom. And whenever you have a carbon-nitrogen bond, nitrogen, even though it has a positive charge, it's a relatively poor leaving group like fluorine. And so we're going to get that carbanion transition state. So therefore, since primary carbanions are more stable than secondary carbanions, the oxygen is going to go for the more stable primary hydrogen because it leads to the more stable carbanion transition state. So it's going to go for the blue hydrogen, and this is going to break, kicking out the nitrogen atom. So we're going to get the same Hoffman product. So the Cope and the Hoffman elimination reaction are Hoffman reactions. They don't produce the Zaitsev product. You get the Hoffman product in both cases. It's just this is a syn elimination reaction and the other one is an anti-elimination reaction. So here's a question for you. what if you have two leaving groups as opposed to one leaving group? So if you use hydroxide, what's going to happen? Feel free to pause the video and try this example yourself. So hydroxide is going to go for the hydrogen that's going to cause the better leaving group to leave. Fluorine is a poor leaving group, so it's going to take more time to get rid of the fluorine atom. But bromine is a good leaving group, so we can get rid of that. Now, because it's a good leaving group, should we remove the yellow hydrogen or should we remove the blue hydrogen? Now, typically, when you have a good leaving group, you're going to get the Zaitsev product as opposed to the Hoffman product. And the blue hydrogen is going to lead to the Hoffman product. That's the terminal alkene. That's the one at the end, which is less stable. So the base is going to go for the yellow hydrogen because it's going to give us the more stable Zaitsev product since we have a good leaving group. So now that we kicked out the good leaving group, now we can remove the poor leaving group, which is going to take a little longer time. So should we remove a yellow hydrogen or the red hydrogen? For one thing, since we have a poor leaving group, it's going to be easier to remove the red hydrogen because it's primary and it's going to give us the Hoffman product, which is usually what we get whenever we have a poor leaving group. Also, if we put a double bond here, having two double bonds next to each other is not good because that's a accumulated diene. That's also known as an allene, and these are unstable. But if we form a double bond here, it's conjugated, which is very stable. So that's what's going to happen. So hydroxide is going to grab the red hydrogen, form a double bond, and expel the leaving group. So now we're going to have a conjugated system. So the driving force for that last step was the stability of the carbanion transition state. The hydroxide prefers to go for the red hydrogen whenever you have a poor leaving group, and also the stability of the product because we have a conjugated double bond system. And so that's going to be the product for this reaction. So now the next thing we need to talk about is E1 reactions, but with rearrangements. E2 reactions do not rearrange because they do not form carbocation intermediates. E1 reactions, however, that's a different story. So let's say if you have a secondary alkyl halide next to a higher substituted carbon, in this case a tertiary carbon, you're going to get a hydride shift. Now, if the secondary alkyl halide is next to a quaternary carbon, you're going to get a methyl shift. So in the E1 reaction, the first thing that happens is that the leaving group leaves. And so we're going to get a carbocation intermediate. Now, this is a secondary carbocation. And the reason why the hydride shift is going to occur because if the molecule rearranges itself by moving the hydrogen, we can get a more stable carbocation intermediate. And that's the driving force for this rearrangement. It's carbocation stability. So the hydrogen is going to move towards the carbocation. And once that happens, the plus charge and the hydrogen are going to trade places. So now we have a more stable tertiary carbocation. And at this point, the base, which is we're going to use water with heat, the base can grab either the green hydrogen or it can grab a red hydrogen or a yellow hydrogen. It has to be one carbon away from the carbocation center. Now, the yellow hydrogen and the red hydrogen are going to lead to the same product. Put in a double bond here and put in one here is the same. If you name it, you're going to get 2-methyl-1-butene. So this is 1, 2, 3, 4. You can see there's a methyl on 2 and a double bond is between 1 and 2. If you name this one, we still have a methyl on carbon 2 and a double bond is still between 1 and 2. So because they have the same name, these products are identical. Now, if we remove the green hydrogen, we're going to get a different product. Let's see if I can fit it in here. If we name it, let's say this is carbon 1, 2, 3, 4. We still have a methyl on 2, but the double bond is between 2 and 3, as opposed to 1 and 2. So this is 2-methyl-2-butene. And notice that this alkene is more stable than the other ones because it's an internal alkene, whereas the other two are disubstituted terminal alkenes. This one is trisubstituted. There's 3 R groups. And the E1 reaction typically produces the Zaitsev product as the major product, which is the one that's most substituted and most stable. So this is going to be the major product. The other two that we drew, these two which are identical, that's going to be the minor product. That's the Hoffman product. So just to sum it up, whenever you have an E1 reaction, it can occur by means of the syn or the anti-elimination reaction. And the major product is usually the Zaitsev product. Now, whenever you have an E2 reaction, for the most part, it's usually anti. The only time you get the syn reaction is with the Cope elimination reaction. The rest is anti-elimination. And to get the Zaitsev product, you need 2 things. You need a non-bulky base and a good leaving group, like a bromine, chlorine, or iodine. To get the Hoffman product, you either need a poor leaving group, like a fluorine or a nitrogen atom, or a bulky base, like terbutoxide. That's going to give you the Hoffman product. Now, let's say if we have a quaternary carbon next to a secondary alkyl halide. So this carbon is attached to 4 other carbon atoms, so it makes it quaternary. And let's say if we have another E1 reaction, but this time, instead of using water, we're going to use methanol with heat. So the first thing that's going to happen is the leaving group is going to leave. And so we're going to get a secondary carbocation. Now, on the quaternary carbon, there are no hydrogens directly attached to it. So we can't get a hydride shift. This time, we have to get a methyl shift. So the methyl is going to migrate and trade places with the carbocation. And so the methyl is over here this time. So now, instead of having a secondary carbocation, we now have a tertiary carbocation. And just like before, well, this time we need to use methanol instead of water. Methanol, which is going to be the weak base, is going to go for a hydrogen that's adjacent to the carbocation. So we can form a double bond anywhere around the carbocation center. But I'm just going to focus on a Zaitsev product. So methanol is going to grab the red hydrogen, and then the carbon-hydrogen bond will break, and those pi electrons will be used to form the alkene, which will look like this. So here we have a very stable tetrasubstituted alkene, and so that's going to be the product for that reaction. So now we're going to go over the E1 acid-catalyzed dehydration reaction of alcohols. So we're going to use a strong acid, concentrated H2SO4. So there's a small amount of water that's in the solution. And we're going to add heat. Heat favors E1 reactions. So here we have a secondary alcohol. If you have a secondary or a tertiary alcohol, it's going to favor the E1 mechanism. If you have a primary alcohol, it's going to favor the E2 mechanism, because it's very difficult to form primary carbocations. So the first thing that's going to happen whenever you add an acid is protonation. Right now the OH is a poor leaving group, but once you add a hydrogen to it, it's going to turn into a better leaving group. And so it's going to turn into OH2. Whenever oxygen has 3 bonds, it's going to have a plus charge. In the next step, the leaving group is going to leave. And so we're going to get a secondary carbocation. And in the next step, we can use water as the base, or we can use HSO4 minus as a weak base. But I'm going to use water. So in the next step, the base is going to grab a hydrogen and form the double bond. And so that's the E1 dehydration reaction. That's how you can convert an alcohol into an alkene. So what if we have a primary alcohol this time? And we're going to use H2SO4 again as our acid. What's going to happen? So we know this time we're going to get an E2 reaction. So in an E2 reaction, there's no carbocation intermediates that are formed. But the first step is going to be the same. Anytime you add an acid, the first step is usually protonation. So now the alcohol is going to turn into a good leaving group. Now in the next step, that's the elimination step. That's where the weak base comes in and removes the hydrogen. In an E1 reaction, we would get the carbocation intermediate. But in an E2 reaction, the base is going to come in, is going to grab the hydrogen, form a double bond, and expel water all at the same time. So that's really the E2 step of the reaction. And in this particular example, there's only one product that we can get, which is 1-butene. Feel free to pause the video and try this example. What do you think is going to happen if we use sulfuric acid? So we have a secondary alcohol, and just as before, the first step is protonation. So because it's secondary, it's going to follow the E1 mechanism. So water is going to leave. And once water leaves, we're going to get a secondary carbocation. So at this point, a rearrangement can occur. Now the question is, what kind of rearrangement will occur? Will it be a hydride shift or something else? Because we do have a tertiary carbon next to a secondary carbon. Now what's going to happen is a ring expansion. When you have a 5-carbon ring, sometimes it can expand to a 6-carbon ring. So this is carbon 1, 2, 3, 4, 5, 6. The bonds between carbon 2 and 6 are going to break. And carbon 6 is going to connect with carbon 1 to form a 6-membered ring. So it's going to look like this. The plus charge, let's put the carbon atoms first. So this is carbon 1, carbon 2, 3, 4, 5, 6. Carbon 1 has the methyl on the outside, which is still here. Carbon 2 is the carbon that now has a plus charge. Now let's understand how this carbocation expansion works. Now imagine if the bond between carbon 2 and 6 breaks. But now those electrons in that bond, it's going to go towards carbon 6. Now the reason for that is because carbon 6 is going to connect to carbon 1. And since carbon 1 has a plus charge, carbon 6 should have the negative charge. Otherwise, the two won't connect. So notice that carbon 6 took both electrons in that bond. So that's going to leave a plus charge on carbon 2. Now, if the carbanion connects with the yellow carbocation, we're going to get the 5-membered ring. But if it connects with the red carbocation, we're going to get a 6-carbon ring. So as you can see, carbon 2 is going to have the plus charge since it lost the bond. And that's why it's going to expand into a 6-carbon ring that looks like this. So carbon 1 has the methyl. Carbon 2 has the plus charge. And then it's 3, 4, 5, 6. So 6 is attached to 1. And so that's the structure that we now have. So what's going to happen next? So we still have a secondary carbocation, but the ring has expanded from a 5 carbon ring to a 6 carbon ring. So we have a more stable carbocation. A 6 carbon ring is always more stable than a 5 carbon ring because it has less steric strength. Now notice that the secondary carbocation is still adjacent to a tertiary carbon. So a hydride shift is about to occur. So now we have a tertiary carbon and we have a 6 carbon ring. So what's going to happen now? At this point we can form the alkene. So water is going to act as a weak base and it's going to grab the hydrogen that's adjacent to the carbocation. That's 1 carbon away. And so we're going to get the alkene. And so our final product looks like this. Now, what is the difference between alpha elimination and beta elimination? A lot of examples that we covered was beta elimination. So consider the alkyl halide that we have here, 2-bromobutane. The carbon that has the functional group, in this case the bromine, is the alpha carbon. The beta carbon is 1 carbon away. So in the E2 reaction, typically you're removing a beta carbon. So that's why this is called a beta elimination reaction, because we're removing the hydrogen from the beta carbon. So if that's a beta elimination reaction, what is an alpha elimination reaction? There's a reaction that you've learned in the electrophilic addition of alkenes where it looks like this. Let's say if you have an alkene and if you add CHBr3 with KOH, you're going to get a cyclopropane ring, and this carbon is going to have 2 bromine atoms. Now this is a step in a mechanism of this reaction that is an alpha elimination step. CHBr3, this is known as bromoform, and we're going to react it with potassium hydroxide, but we only need the hydroxide part. Now the carbon has 3 electronegative atoms attached to it, and typically most CH bonds are usually not acidic, but in this case the hydrogen is fairly acidic enough that the hydroxide can deprotonate or remove that hydrogen. Whenever you add an electronegative atom to an acid, the hydrogen on the acid becomes more acidic. It's easier to remove the hydrogen. So this base is strong enough to deprotonate hydrogen. And so we're going to get a negative charge on the carbon. So this is a carbanion. Now it turns out that something interesting is going to happen. This carbanion, this carbon with a negative charge, is going to expel a bromine atom. And it happens spontaneously. And so you get what is known as a carbene. Notice that carbon doesn't have a negative charge anymore. In the carbene form, it's neutral. And so by expelling the bromine atom, it loses that negative charge. So this reaction is called an alpha elimination reaction because we remove the hydrogen and the bromine on the same carbon, the alpha carbon. So it's called an alpha elimination reaction. Here's another reaction that's similar to an E2 reaction. Let's say if you have an alkyl halide, but that has 2 bromine atoms. Instead of using a strong base like hydroxide, you can use sodium iodide and acetone, or zinc with acetic acid and sodium iodide. The iodide ion is going to attack the bromine atom. And as that happens, the carbon-bromine bond breaks. It's going to form a double bond and expel the other bromide or bromine atom. So you're going to get an alkene. Let's say the iodide was paired up with sodium. So now we're going to have IBr. Those two are together. And NABr. So this reaction, it looks similar to a typical E2 reaction, but with no hydrogen instead. So that's another reaction to know. The last reaction that we're going to talk about is the E1CB reaction. And it's useful for removing poor leaving groups, particularly hydroxyl groups. It works pretty well if the hydroxyl group is like 2 carbons away from a carbonyl group. The reason for that is this red hydrogen, which is known as an alpha hydrogen with respect to the ketone, that hydrogen is relatively acidic because it's stabilized by resonance. At least the conjugate base is stabilized by resonance. So let's say if we add a strong base like hydroxide. Hydroxide is going to remove the hydrogen, forming a carbanion. So let's draw the resonance structure. This carbanion can use its electrons to form a double bond, causing a pi bond to break. And so that's why the alpha hydrogen was fairly acidic, because the conjugate base is stabilized by resonance. So this is called an enolate ion. Now what's going to happen next? This enolate ion could use one of its lone pairs to form a double bond, causing this double bond to move here, expelling the hydroxyl group. So we're going to regenerate the ketone, but we're going to form a double bond over here. So basically, we got rid of the hydroxyl group and the hydrogen that was here. So we remove water. This is an example of an E1CB reaction. So now you've seen it all. You've seen the E2 reaction, the E1, the E1CB, and you've seen plenty of examples on how to use them, when to apply them. We talked about the rate law, potential energy diagrams, and hopefully you found this video to be educational. So thanks for watching and have a great day.